Hi, I'm Yuval Atzmon from Bar-Ilan University and NVIDIA Research. I will describe our work on generalized zero-shot learning that was accepted to CVPR. Zero-shot learning is about learning to recognize new classes just from a textual description, without seeing any training examples from these classes. For example, if I tell you that a jackalope is a rabbit that has horns, could you recognize the jackalope? Even though you've never seen a jackalope, you could easily recognize it. Now, this is important because there aren't any good ways for learning from a description. The mainstream models in deep learning demand large-scale labeled datasets that are expensive to collect, and it just doesn't scale to many classes. We simply cannot collect hundreds of images per class when there are tens of thousands of classes. At the same time, people can learn from descriptions, like when someone teaches us something new or when we learn by reading books. We want algorithms that can do that as well. For example, learn from Wikipedia text. So, more formally, in zero-shot learning, we have a training set of labeled images from thin, well-sampled classes, and each class is accompanied with a description. At test time, we wish to recognize images from new unseen classes, just based on their description, without seeing any training examples for them. Now, briefly, in zero-shot learning, we learn a similarity score between an image and a description. Then, given a test image from a new class like this one, we select the description that best matches the image. Here it is rabbit with horns. We then predict the class that matches that description. This work specifically focuses on generalized zero-shot learning. Here we train on the same set of labeled images, but at test time, the image we see is either from a new unseen class like before, or from one of the seen classes that we've trained on. Now, this change in evaluations seems minor, and indeed it was hardly discussed during the first 7 years that people worked on zero-shot learning. But about 3 years ago, new publications reported that standard zero-shot learning models fail to recognize the new classes when they are mixed with previously seen classes. For example, if we take this image and feed it into a model, then the scores of the seen classes would be more dominant than the scores of the new classes. This new problem corresponds with some very hot topics. First is poorest correlations. Models may favor seen classes because they learn to rely on unstable correlations found only in the training data of the seen classes. Since the spurious correlations are missing from the new classes, the model tends to predict one of the seen classes. This brings us to domain adaptation and distribution shift. Basically, we want to have a robust prediction on two domains simultaneously. A domain where we collected training data from some observed distribution, and a domain with a different distribution that has undergone some change and we don't have any examples for it. And this finally leads us to an extreme case of imbalanced data. Here, some of the classes have many training examples and others don't have any. And unfortunately, generalized zero-shot learning suffers from all of these issues. One previous approach to generalized zero-shot learning is called calibrated stacking by Chow and colleagues. Here, they reduce the level of confidence on the seen classes by subtracting a constant value from their scores. Liu uses an entropy-based regularization term, and another method which became popular is based on generative models. Basically, the idea is to use the descriptions to hallucinate images of new unseen classes. This way, One can generate synthetic images and train a standard classifier on a dataset that has both seen classes and new unseen classes. So here's our approach. It is inspired by models of fluent reading in cognitive psychology. Let's start with an example. Take a moment to read the next sentence. When reading fluently, we process a complete word at a time. When we encounter an unfamiliar word like absquatulate here, we pause, understanding that something is wrong, and instead we use a reasoning system that composes the new word from its syllables. And this corresponds to three modules: an intuitive fast module for processing known words, anomaly detection, and a reasoning model based on composing primitive properties. Similarly, our approach has an expert module for seeing classes, which is a standard classifier, an expert for new unseen classes, which is a zero-shot learning classifier, and a binary gator that weighs them both. And finally, to combine the prediction, we use the law of total probability. But still, there are two difficulties with this approach. The first relates to the fact that classifiers tend to make predictions that are overconfident when they see an image that they should not be able to recognize. Previous reports show that even random noise can be classified as 80% confidence for a cat. Instead, for an out-of-distribution image, we wish to have a conservative prediction which is more uniform across classes, since they are all equally wrong. To achieve that, we add a uniform prior to the predictions during inference. This prior spreads the mass of their softmax distribution more uniformly across the classes. We weight the prior using a parameter lambda, where we set lambda adaptively for each input image by using the gator's belief. This has a probabilistic interpretation. Let's say the unseen expert sees an out-of-distribution sample, which is a seen class image. Given that we know it is an out-of-distribution image, the best distribution of scores among the unseen classes is a uniform distribution, because they are equally wrong. Then, using the law of total probability, we obtain the following probabilistic model that allows smoothing using the gator belief. For example, here the gator does not trust the experts, and P of U of unseen classes is low, and 1 minus P of U is high. And we can obtain the distribution on the right. This process is called smoothing, and here you can see how the smoothing varies as a function of the gator belief. The second challenge is how to train the gator without any image from the unseen classes. Our solution is to inspect the softmax output of the two experts and learn how each one of them responds to images from either seen classes or new unseen classes. And since there are no examples from the new unseen classes, we simulate them by leaving out part of the training classes so the experts can treat them as new classes. In conclusion, our model has four stages. First, calculating class confidence scores for each expert. Then, predicting the seen or unseen domain with the gator, smoothing, and finally combine the predictions using the law of total probability. We tested our approach on four benchmark datasets: a dataset for fine-grained bird recognition, animal recognition, visual scenes, and flowers. The popular evaluation metric is the harmonic mean between the accuracy of the new classes and the accuracy of the scene classes. The table shows the results for zero-shot learning models from the last year and three baselines. DCN is the baseline with regularization for entropy. LAGO is the zero-shot expert we use, and it is not that great on the generalized zero-shot learning task. LAGO with calibrated stacking of chow improves performance, but still we can do better. Our model, which we call Cosmo, outperforms all other baselines with a very large margin, and it is the first standard zero-shot learning model that outperforms classifiers that are based on generative models. This means that the current generative models solve a much harder problem than needed, because it is hard to generate good synthetic examples, and our work shows that they do not add any new information. We can also examine the results in a diagram that shows the trade-off between the accuracy of scene classes on the x-axis with the accuracy of the new unseen classes on the y-axis. The triangles mark the results of standard models for zero-shot learning. They all favor the scene classes. The X symbols mark classifiers that are based on generative models. They favor new classes at the expense of scene classes. Ideally, we wish to perform in the upper right corner, doing well on both seen and unseen classes. Lago, our zero-shot learning expert, is indeed not that great in the generalized zero-shot learning task. And as mentioned earlier, using Chow et al., we can bias it toward the new classes. Finally, our method, Cosmo, is better or equivalent to all other methods. The curve with the blue dots is obtained by varying the gator's decision threshold, which allows us to choose to bias the predictions more toward the new classes or more toward the seen classes. Notice that we carefully selected the optimal operating point with cross-validation. Last, we see a similar trend with other datasets. So let's wrap it up. Generalized zero-shot learning is a setting that requires robust prediction across different domains. Our approach softly combines domain experts and knows how to carefully handle predictions of overconfident experts. Our results show that with Cosmo, standard classifiers can outperform classifiers that are based on generative models. Thank you for listening. Here is a link to our project page with the paper and code.